Good morning, all. In the previous lectures, we have already discussed about the economy of power plant, and there were few points and few definitions which must be remembered. So, in this lecture, we are going to about the tidal energy. Okay? So, learning objective of this lecture is to understand the concept of tidal energy. And after this lecture, I'm expecting from student that student will be able to understand what is tidal energy, how it is defined, what is the utilization of tidal energy, and what are the advantages of and disadvantages of utilizing of tidal energy. So next point is your content. Content is your tidal energy, source of tidal energy, advantages and disadvantages. These are the contents of my presentation or this lecture. What is tidal energy? First, we have to understand what is tidal plus energy. So everyone knows what is energy. Energy is if you talk in the terms of electrical term, that it is always denoted in kilowatt hour. Okay. So by using tidal, we get the energy from tidal. So what is tidal energy? Tidal power facilities harness the energy from the rise and fall of tides. Okay, when you can see in the sea areas, tides come, like you can say high waves of sea comes and that goes down. So when it is rise, it has some energy and fall of tides. So by using this energy, we can generate the electricity. So there are two types of tidal plant facilities. One is your tidal barrages, second is your tidal current turbines. So ideal sites are located at narrow channels and experience high variation in high and low tides. So basic physics of tides. So one is your gravitational pulse of the sun and moon and the pull of the centrifugal forces of rotation of the earth moon system. So first we have to understand that how this tide are created and how it works and what is your tidal energy. So there, some gravitational force which is coming from the sun and moon. So they pull of the centrifugal forces of rotation of the earth moon system. So you can see in this picture, this is your earth and this is your moon. So there is some, gravitational force towards moon and sun. So gravitational force bulge of water. So balance point or center of mass of the earth moon system is this, and centrifugal force, this is your centrifugal force and this is your gravitational and centrifugal forces. So two resultant bulges of water. So when a landmass lines up with the earth moon system, the water around it is at tide, high tide. Okay. When a landmass is at 90 degree of the earth moon system, then the water around it is at low tide. So there are two high tides and two low tides during each period of rotation of the earth. And spring and neap tides depends on the orientation of the sun, moon, and the earth. So high spring tides occur when the sun and moon line up with the earth. This occurs whether they are either on same or opposite side. So low neap tides occur when the sun and moon lines up at 90 degree to each other. Flood currents moving in the direction of the coast. So EBB currents are the current receding from the coastal areas. So tidal barrage, that is utilization of potential energy. Tidal barrages are typically dams built across an estuary or bay, consist of turbines, sluice gates, embankments, and ship locks. So sluice gates, that is a sea. This is a barrage, and you can connect one turbine over here. So when tides come at its high tides come, then the water, hit to the turbine, and turbine start to rotate, and this turbine is connected to the generator. So this is your sea. These are the gates, and land, high water mark and basins. So single basin system, there are two type of system. One is your single basin system and another one is your double basin system. So EBB generation during flood, tide basin is filled and sluice gates are closed, so trapping water. So gates are kept closed until the tide has ebbed sufficiently and the turbines start spinning and generating electricity. And flood generation, the basin is filled through the turbine, which generate at flood tide. Two-way generation, sluice gates and turbines are closed until near the end of the flood tide, when water is allowed to flow through the turbines into the basin, creating electricity. So at the point where the hydrostatic head is insufficient for power generation, the sluice gates are opened and kept open until high tide, when they are closed. So when the tide outside the barrage has dropped sufficiently, water is allowed to flow out of the basin through the turbines, again creating electricity. So this is the procedure by which you can create the electricity from tidal energy. Next is your double basin system. There are two basins, but it operates similar to an EBB generation. Single basin system, the only difference is a proportion of the electricity is used to pump water into the second basin, allowing storage. Current sites of tidal barrage. France, the first and largest tidal barrage power plant, constructed between 1961 and 1967, situated on the Rance River. So you can easily understand that what is your tidal energy. Now, pros and cons of both tidal power facilities. So you can use your tides to generate the electricity, but there are some pros and cons for this facility. So, what is your tidal barrage? It mature technology that has been around for nearly 50 years, and you can get a reliable energy source from the tidal energy source. But the construction cost is very high for the tidal energy, and there are environmental impacts on marine life. So, low power output in comparison to other energy source like coal and nuclear power plants. So tidal current turbines able to utilize both EBB and flood tides. Tidal category current turbines are not large, massive dam structure, but tidal currents turbine technology is young in its development. Installation and maintenance challenges. Environmental impacts are still being tested. These are the references of this tidal energy. So basically, what is happening by using the tides, you can generate the electricity, but there are some advantages and disadvantages. And this tidal energy is utilized in at the coastal areas. So this is the basic physics of tides. Uh, First, Draw the load curve and select suitable generators units from the 10,000, 20,000, 25,000, 30,000 kilovolt amperes. So prepare the operation schedule for the machine selected and determine the load factor from the curve. So first what we have to do, we have to draw the load curve. So load curve can be drawn. You have to take time on x-axis and megawatt, which is your load in megawatt, which is on y-axis. Okay. Now from the table, we can see that from 6 a.m. to 8 a.m. you required 20 megawatt. Okay. So this is only for 2 hours. Okay. So uh, for 2 hours you require 20 megawatt, but for 8 to 11 more, 3 hours more, so you required again 20 megawatt from 6 to 11. So time, this is time in hours. For 0 to 8 hours you require 20 megawatt. Okay, 0 to 8 hours you require 20 megawatt. 2 hours, and this is your 6 hours. So you require 20 megawatt load. Now we come to 40 megawatt load. So 40 megawatt load, 3 hours plus 2 hours, for 5 hours you require 40 megawatt load. So you can see for 5 hours, 8 to 9, 9 to 10, 10 to 11, and 11 to 12, you required 40 megawatt. Then 50 megawatt you required 11 to 16, means 11 a.m. to 4 p.m. you required your 50 megawatt. 4 p.m. from 11 a.m. to 4 p.m. you required 50 megawatt. Then from 4 p.m. to 7 p.m. you required 35 megawatt. So from, this is your 35 megawatt load, which is required from 16 to 20 hours. Then 19 to 22, from 7 p.m. to 10 p.m. you required 70 megawatt. So from 10 p.m. to next hours you required 70 megawatt. Again it is getting down, so you require 10 p.m. to 12 midnight you required 40. 12 p.m. to midnight you required 40 megawatt. So this is your load curve. Okay, and now in load duration curve we arrange the load in descending order. First we calculate the maximum load, after that the load which is less than your maximum load. So in descending order we always draw the load duration curve. So this is your load curve. Now we can calculate the unit generated per day by the area under of this curve. Okay, so load under area of the load duration load curve is always give the unit generated in a day. So you can easily calculate the area of this rectangle. Okay, so 20 into 8. Next 40 megawatt is required for 3 hours. Like this 50 required for 5 hours. Then 35 megawatt required for 3 hours. 70 is required for 3 hours. 40 megawatt is again required for 2 hours. Okay. So you can easily calculate the maximum, uh, you know, the unit generated per year. So it is 925 into 10 to the power 3 kilowatt hour. This much of energy is generating through this power plant in a day. Okay. Now we next come to this point that what is your average load? So average load can be calculated divided by this unit by 24 of a day. So you can easily calculate the average load. Next, load factor. The formula of load factor, I have already told you that average load upon maximum demand. So the average load of this substation is your 38,541.71 watt, which is divided by your maximum demand, which is your 70 megawatt. So you can easily calculate the load factor, which is your 55.06%. Now it is saying that you have to select the suitable generator unit through the machine. So we can assume that how can we select the number and size of unit. So we are assuming that the power factor of a machine is your 0.8. Now the amount of power generating from units available will be 8, 16, 20, and 24 megawatt. This is your 4 unit. Okay. So there can be several possibilities while selecting the size and number of units. So we have to take, we have to consider that the base load must be continuous, and for this base load, the number of units which is suitable for base load must be, operated, and the maximum demand, which is your 70 megawatt, the unit must need the maximum demand also on the station. So there should be overall economy when you are selecting the units for generations. So we are taking 4 sets of 24 megawatt. Each may be chosen. So 3 sets will meet the maximum demand. Okay, we 3 set it actually 2 sets, if you are taking 2 sets of 24 megawatt, it will be 48, and if you are taking 3 sets of 24 megawatt units, then it will be 3 72 72 megawatt. So if you want to meet your maximum demand in a generating station, then you have to take 3 units, which is each of 24 megawatt. So next point is your operation schedule. How will you decide the operation schedule? So from the load curve, you can see that set number one, 24 megawatt. So 24 minimum load is your 20 megawatt. Okay, minimum load is your 20 megawatt, and 1 unit will run for 24 hours. Now for next 8 hours, from 8 hours to midnight, you can see that 8 hours to midnight. Okay, 8 hours to midnight. At least you need set number 2. Set number 2 will run for 8 hours to midnight, and set number 3 will run for 11 hours to 16 hours, and again from 19 hours to 22 hours. Okay, from 11 hours to 16 hours, and from again 19 hours to your 22 hours. So these are the 3 sets by which you can run the power plant. Now the next question is, a generating station is to supply 4 regions to load whose peak load are 10 megawatt, 5 megawatt, 8 megawatt, and 7 megawatt. So the diversity factor at the station is 1.5, which is given, and the average annual load factor is also given, which is your annual load factor is 60%. Now you have to calculate the maximum demand of the station. and annual energy supplied by the station, and the suggest the installed capacity and the number of units. So you can see that the load which is are given is your 10 megawatt, 5 megawatt, 8 megawatt, and 7 megawatt. Diversity factor is given. The formula for diversity factor is equal to sum of individual maximum demand is divided by maximum demand of the station. So you can easily calculate the maximum demand on the station by using this diversity factor. Okay, so the peak load of individual load is given. So the peak load of individual sum of maximum demand of all region, which is given 10 plus 5 plus 8 plus 7, and it is divided by 1.5. So you can easily get that the maximum demand on station is 20 megawatt, right? Now come to the next point, annual energy supplied. So annual energy, the unit of energy is kilowatt hour. Okay. So first you have to know about your kilowatt or megawatt generation, which is your 20 megawatt, and you know the load factor formula is equal to average load, which is divided by maximum demand. So the average load can be calculated by generated calculated. So the average load can be replaced by unit generated per annum divided by hours. So you can easily calculate that the unit generated per annum, because load factor formula is equal to unit generated per annum upon maximum demand into hours in a day. So unit generated per annum is equal to maximum demand, which is your 20 megawatt. Load factor is your 0 0.6, and hours in a year is 8760. So you can easily calculate the unit generated per annum, which is 105.12 into 10 to the power 6. Now let's come to the next point, the installed capacity of station and how much how what must be the number of units. So the installed capacity of station should be 15% to 20% more than its maximum demand, so in order to meet the future growth of the load. So taking installed capacity to be 20% more than the maximum demand, you can easily calculate the installed capacity, which is equal to 1.2 into maximum demand. Okay, so you will get 24 megawatt. So installed capacity of a generating station is your 20 megawatt, and maximum demand is your 24 megawatt, and the maximum demand is your 20 megawatt. So suitable unit size are 4 and each of 6 megawatt capacity. Now we come to the next numerical. So the question is, a base load station having a capacity of 18 megawatt. Base load station means that the load which is uh, decided for this station must be supplied continuously. Okay, so it is your 18 megawatt, and a standby station having a capacity of 20 megawatt share a common load. So find the annual load factors and plant capacity factors of two power stations from the following data. So the annual standby station output is 7.35 into 10 to the power 6 kilowatt hour, and the annual base load station output is 101.35 into 10 to the power 6 kilowatt hour, and the peak load on standby station is your 12 megawatt, and hours of use by standby station per year is 2190. So first you have to calculate the installed capacity of standby unit. So installed capacity of standby unit is your 20 megawatt. So you can convert this megawatt into kilowatt. So it becomes 20 into 10 to the power 3 kilowatt. Now the capacity, installed capacity of base plant is, which is given 18 megawatt. So it can be your 18 into 10 to the power 3 kilowatt. Now, standby station annual load factor. So you know the formula for load factor is equal to the unit generated or average load upon maximum demand. If you are taking average load in terms of energy generated, then the formula becomes kilowatt hour generated per annum upon maximum demand into annual working hours. So the annual load factor can be calculated by this, and the kilowatt generation from the standby is given 7.35 into 10 to the power 6, which is divided by its maximum demand, which is your 12 megawatt peak load on is this is your 12 megawatt, and annual working hours is your 2190, because this standby is using only for 2190 hours in a year. So you can easily calculate the annual load factor for standby station, which is your 28%. Okay. Now, annual plant capacity factor. So the annual plant capacity factor, the formula is your average load divided by installed capacity. So average load can be written in to the terms of your unit. So the plant capacity is installed capacity is your 20 megawatt for your standby station, and it can be calculated by this formula. So the plant capacity factor is your 4.2%. Now we come to the base load station. So it is reasonable to assume that the maximum demand on the base load station is equal to the installed capacity, which is your 18 megawatt, because it will continuous supply the load, which is 18 megawatt. So it operates throughout the year for 8760 hours. I have already discussed that what is base load and what is peak load. Base load is which is continuously supplying to the consumer throughout the year. Okay, it can't uh, be more than your 18 megawatts. So maximum capacity, or you can say maximum demand of this base load station is your 18 megawatt, and one unit is always standby. When you required maximum demand, then you can use that particular standby unit. So maximum demand for the base load station is 18 megawatt. So it operates throughout the year for 8760. So you can easily calculate the annual load factor, which is equal to unit generated through the power plant, which is your 101.35 into 10 to the power 6 kilowatt hour, divided by total time 8760, and multiply by your maximum demand. So this is your 64.2%. So as the base load station has no reserves above peak load and it is in continuous in operation, therefore its capacity factor is also 64.2%, which is more than your standby unit, because standby unit is always come into the picture when you required peak load, and base load is continuous in operation. That's why its capacity factor is higher than your peak load or standby unit. Now this is very important question, so we will discuss about this numerical. uh, the problem is given that the load duration curve for a typical heavy load being served by a combined hydro steam system. So hydro is also connected and steam power plant is also connected, may be approximated by a straight line, and maximum and minimum loads being 60,000 kilowatt and 20,000 kilowatt respectively. So the maximum load of these hydro system steam system is 60,000 kilowatt, and the minimum load is your 20,000 kilowatt respectively. So the hydropower available at the time of minimum regulated flow is just sufficient to take a peak load of 50,000 kilowatt hour per day. So it is observed that it will be economical to pump water from the tail race to the reservoir by utilizing the steam power plant during the off-peak periods, and thus running the station at 100% power factor. So determine the maximum capacity of each type of plant. Assume the efficiency of steam conversion to be 60%. So the steam which is converting from water is only 60%. And the graph is given over here. So this is your minimum demand, which is your 20,000, and this is your maximum demand, which is your 60,000. Okay. So the slope is BC. Now you can see that the OCBA represent the load duration curve for the combined system. OCBA, OCB and A, which is representing the load duration curve from ascending order to descending order. Okay. Now the total maximum demand is 60,000 kilowatt. You can see over here, and the minimum demand is your 20,000 kilowatt, which is presented by OD. This is OD minimum, and CD is your maximum demand. Now, capacity of a steam plant is OE. This is the capacity of a steam plant, and the capacity of your hydropower plant is your EC. This is the capacity of your steam plant, and this is the capacity of your hydro plant. And the area CHI, this area is represent the energy available from hydropower plant in the low flow period. If flow is low, then this is your energy which is available to the hydropower plant CHI. Now, area FGB, this is the area FGB. This is your off-peak period. So, the off-peak period energy available from steam plant. Okay, and this is the energy which is available for hydropower plant, and this is the energy available from steam plant. So obviously the energy of hydro plant represented by the area HEFI. This is the energy of hydropower plant, and available from reservoir has been supplied by steam plant represented by area FGP. Okay, so as steam electric conversion is 60%, so the area HEFI is equal to 6 point into area FG. So you can easily calculate. Now area HEFI is equal to area CFE, area CFE minus area CHI. Okay, so the area CFE can be calculated. Area CFE can be calculated 1 by 2 into x into y, horizontal into perpendicular because it is a triangle, and area CHI can be minus, and the area CHI is already given, that the hydropower available at the time of minimum regulated load is just sufficient to take a peak load of 50,000 kilowatt hour per day. Okay, so this is your low flow period. So you can calculate area HEFY by this equation. Now, area FGB, this is for your steam power plant. You can see FGB. So 1 by 2 EG minus FE. So EG minus X. And this is the area where you can calculate GA minus BA, GA minus 20,000. So 24 minus X and GB is your 40,000 minus Y. Y is your uh, this height, and this is equal to Y. Okay, so you can easily calculate the area FGB by using this equation. And when you putting the various values in expression 1, we get FG into GB XY minus 50,000. So the area FGB is equal to the area HEFI. So 1 by 2 XY minus 50,000 is equal to 0.6. 1 by 2, 24 minus X, 40,000 minus Y. And by solving this equation, you will get the value of X and Y. So putting Y is equal to 40,000 X upon 24 in expression third and second, we will get X is equal to 12, and the capacity of the hydro plant is 40,000 into 12 divided by 24, which becomes 20,000 kilowatt. And the capacity of a steam plant is 60,000 minus 20 kilowatt, which is equal to 40,000 kilowatt. So by these equation, you can easily calculate the uh, capacity of hydropower plant and the capacity of steam power plant. Now, the next question is the annual load duration time for a typical heavy load is being served by a steam station and a run-off river station and a reservoir hydroelectric station is shown in figure 3.16. Is as follows, and the steam is runoff river ratio and reservoir ratio is given. The runoff river station is capable of generating power continuously and works as a base load station. The reservoir station works as a peak load station. Determine the maximum demand of each station and load factor of each station. So from the diagram that you can see that ODCA is the annual load duration curve. ODCA is your annual load duration curve. This is your maximum demand. This is your minimum demand. This is your reservoir hydro station. This is for your steam station. And this is your runoff river station. So the energy supplied by the reservoir plant is represented by the area DFG. DFG. Okay. And the steam station by the area FGCBE and the runoff river area OEBA. And the maximum and minimum loads are 320 megawatt and 160 megawatt respectively. So 320 megawatt and 160 is your minimum load, Unit generated per annum, area in kilowatt under annual load duration curve. So you have to calculate this area, and you can easily get the generated unit by per annum, which is equal to 2100 02.4 into 10 to the power 6 kilowatt hour. So this is the unit generated per annum. As the steam plant, runoff river plant, and hydro plant generated unit in the ratio of 7 ratio 4 ratio 1. So therefore, unit generated by each plant is given by this is the total unit which is generated by this by three plants. So individual unit you can calculate by this formula, and you will get the individual unit which is generated by power plants. Now maximum demand on runoff river area. Runoff river area is your this area. So OEBA maximum demand, which can be calculated by this formula. So OEBA is divided by OA. You will get the maximum demand which is fulfilled by runoff area, runoff river power plant. So 700.8 into 10 to the power 6 kilowatt units are generated by the runoff river plant. When you divide it by the total year time or total hours in a year, then you will get the maximum demand on runoff river plant. Now, suppose the maximum demand of reservoir plant is Y megawatt and it operates for X hours, then you can written is Y upon 160 is equal to X upon total hours in a year, and X is equal to you can get 8760 Y upon 160. So you can use unit generated per so unit generated per annum by reserve plant is area in kilowatt hour DFG, and you can easily calculate by this formula per annum by reservoir plant, which is your hydropower plant. So unit generated by reserve plant are this, and the maximum demand on the reservoir station is at 80 megawatt, and maximum demand on the steam station is your 320 minus 80. This is your 160 megawatt, which can be calculated by this curve. Okay, so you can easily calculate the maximum demand of steam station, maximum demand of reservoir station. Now, load factor of run of river plant is equal to 100% because it is supplying your base load, and it will run for throughout the year. So its load factor is your 100%. Now the load factor of reservoir plant, this is your unit generated and divided by maximum demand into 8760. This is your 25%, and the steam plant load factor is your 87.5%. So you can compare these three plants and their load factors. Okay, so maximum load factor is for your runoff river plant. After that is your 25%, which is for your reservoir plant, and load factor of a steam plant is your 87.5%. Now, a substation has a daily load cycle as under 260 megawatt for 6 hours, 200 megawatt for 8 hours, and 160 megawatt for 4 hours. So different loads are given over here, and you have to calculate if the substation is equipped with four sets of, it has four units which has 75 megawatt each capacity, and you have to calculate the daily load factor, plant capacity factor, and daily requirement if the calorific value of oil used, you are using oil as the as as a fuel, and instead of coal. So value of oil used were 10,000 kilocalorie per kilogram, and the average heat rate of station were 2,860 kilocalorie per kilowatt hour. So this is very important that the problem in which we have given a load cycle that 260 megawatt is required for 6 hours, 200 megawatt is required for 8 hours, 160 megawatt is required for 4 hours. So you can calculate the units which is generating by the substation. So you can use unit supplied per day, which is 260 into 6 plus 200 into 8, 160 into 4 plus 100 into 6. So you will get 4,400 into 10 to the power 3 kilowatt hour. This is the unit supplied per day. And daily load factor, which is your, you can calculate by the formula, load factor, which is your um, average load divided by your maximum demand. So maximum demand is your 260 megawatt, and unit or average load is your 4,400 into 10 to the power 3. So daily load factor is your 70.5%. Now, plant capacity factor. So as you know, the plant capacity factor is equal to average load divided by plant capacity. So plant capacity is your, it has four units. So plant capacity, station capacity is your 75 into 10 to the power 3 into 4, which is your plant capacity. And this is your average load, which is in kilowatt. So you can divide this average load divided by station capacity. You will get 61.1%, which is your plant capacity factor. Now, next point is your heat required per day. So heat required per day can be calculated that the calorific value is also given. Calorific value is given. So this is equal to 2860 into 4,400 into 10 to the power 3, which is your average load, and this is your plant heat rate. Okay, so this is your heat required, uh, which is in kilocalorie. And if you want to calculate the fuel, then you have to divide this heat rate by 10,000 kilocalorie per kilogram of calorific value of this fuel, and you will get the fuel which is required is in kilogram. So there are few more numericals. We will discuss it in our next lecture, and there are some, you know, some numerical problems by which you are able to understand that what is basically your load curve and how it works and how it is important for power generation. And there are a few MCQs. One is your a load curve is plot of, which is load versus time. Second question is for economy in generation power. You need plant utilization factor must be high. Which of the following category of consumers can provide highest load factor, which is your continuous process plant? The load of a consumer is generally measured in terms of kilowatt. The normal connected load of a domestic consumer is usually up to 10 kilowatt. Load factor during a period is your average load divided by maximum load, and the demand factor is your maximum demand upon connected load. And what is the advantage of sectionalizing of power plant? It is necessary for high reliability. Whenever you require that, whatever is your demand, it must be fulfilled. So for high reliability, the sectionalizing of power plant is required. The area under the load curve represents number of units generated, and the which of the following is equal to the maximum demand. So the peak of the load curve is your represent always your maximum demand, and load duration curve. Load duration curve is always drawn from descending to ascending order. So the number of hours for which a particular load lasts during a day, which is represented by load duration curve. So this is all about your load curve, load duration curve, and some other factor which is important for your analysis of your substations. Thank you.